All right, so we'll round up tonight's videos with something that actually isn't implicit differentiation. Um, it's a good problem that looks at taking derivatives, first and second derivatives, and seeing how they relate to the function to determine whether the function is increasing, decreasing, concave up, or concave down. So we start off with our function here, and we want to show this and show that. So this is really just the product rule and chain. Um, so let's start with, well, let's just start where we start. The derivative. Well, we've got my first function and then my second function. So the derivative of my first function is 2x times my second function plus the derivative of my first function times the derivative of my second function. Well, the derivative of e to a function is e to the function times the derivative of the function. And that was using the chain rule. Just maybe to pull this over here, we've got f being e to the x, g being negative x, f prime is e to the x, g prime equals -1. So if we have f of g of x, the derivative of that is going to be e to the negative x times -1. Okay, so when we want to show that this equals that, well, all we need to do is factor out an e to the negative x. And I forgot about this minus sign, so this really should have been a minus. Okay, now let's take the second derivative. Well, to find the second derivative, we could use the product rule where here's my first function, and that whole thing is my second function. So it's going to be the derivative of the first. So the derivative of the first is e to the negative x times -1. So that's the derivative of the first times the second plus the first times the derivative of the second, 2 minus 2x. Well, to show that that equals this, let's first distribute this -1 into here. And when we do that, we get e to the x times -2x plus x squared plus, oh, that was a negative x, e to the negative x times 2 minus 2x. So we could factor out an e to the negative x. And we have -2x plus x squared plus 2 minus 2x. And combining and writing in descending order, we get e to the negative x times x squared minus 4x plus 2. Good. Uh, we showed that. So we showed this, and we showed this. And now let's use these to answer the next question. And the next question says, for what x, so for what values of x is f increasing? We'll answer that, and then we're going to answer when is f concave down. So when is f increasing? We know f is increasing when f prime is greater than 0. Okay, well, so if we look at f prime, even though it has that e to the negative x, e to the negative x looks something like that, but it's always positive. So it will always make f prime greater than 0. So the only way that f prime is going to be less than 0 is going to be because of this. So if we think about what that looks like, if we were to graph this, um, x 2 minus x, is that right? Yep. So what does that look like graphically? It has a 0 here, and it has a 0 at 2, and it's shaped like that. So the only values for which that is going to be positive are right up here, and that interval is when x is between 0 and 2. So between 0 and 2, this is positive, which makes this positive, and that if that's positive, then f is increasing. What about for f to be concave down? Well, f is concave down when f double prime is less than 0. So all these rules that we were looking at in chapter 2 now need to be just kind of ingrained in your head. Um, but but now we just kind of replace the intuitive graphical understanding with a real algebraic analytical approach. So we need to find out when the second derivative is less than 0. So here's our expression for a second derivative. We know that this chunk, e to the negative x, is always going to be positive. So we need to know, when is that negative? Well, when is that going to be negative? It certainly doesn't factor nicely. We know that um, that graph is going to be, let's see, we know that that graph is going to be concave up because the leading coefficient is positive. And so to find out the zeros, you go negative b plus or minus the square root of b squared minus 4ac, so 4ac all over 2a. So all over 2. And what does this simplify to? Well, this is going to simplify to 4 plus or minus the square root of 16 minus 8, or 8 over 2, uh, which simplifies to 4 plus or minus 2 root 2 over 2, which equals 2 plus or minus root 2. And those are my zeros. So I know that my function is going to have zeros at 2 minus root 2 and at 2 plus root 2. So when is it going to be concave down? Well, it's going to be concave down for this entire piece right here. But the question is, um, we're looking for this specific range. And we know that 2 root 2 plus root 2 is kind of beyond 3. So when my function is going to be concave down is going to be from this first 0 all the way until 3. So it's going to be from, my function is going to be concave down when x goes from not including, and these should have been not including as well. So from not including to minus root 2 all the way up until 3, including 3. And we can include 3 because of that. So just to see if that answer that we found makes sense, we said that f was increasing from 0 to 2, and that it was concave down on the following interval. So let's see, we said this, copy. And if we go to the next page, here's an actual graph of that function. And so that blue piece is when we said the function was increasing. So this is when f is increasing, and in fact, it certainly is. From 0 to 2, it is increasing. And then this piece here, this is where we said it was f was concave down. And if we look at our function, it's from 2 minus root 2, what is that? That's like 0.6 or something like that. So roughly 0.6 to 3. And that's actually, we're concave up until about this point, till about 0.6. And then to 3, where our function stops being defined, we're concave down. So both of these graphical approaches confirm that we were in fact right, which is what we like to be. Okay, so that's it. That was a lot. This stuff is hard. It's tricky. So do your best to trying to understand it.